So in this video, we'll look at the second way to find the behavior around a critical number of a function f. Please recall the meaning of critical numbers of a function f. Usually, you need to find the first derivative f prime first, and you have to solve for the equation f prime equals 0 or see the value of x such that f prime is undefined. So in a previous video, we found the behavior around the critical number of a function f by using the first derivative test and corresponding sign table of f prime. And this method is the second one. It is called the second derivative test. The reasoning behind the second derivative test is that, if you recall, if you're able to find the f double prime, which is the second derivative, if the f double prime is positive, the fact is that we expect the shape to be concave up for the graph of y equals f of x. And similarly, if the f double prime is negative, we expect the shape to be concave down for the graph of y equals f of x. And we'll make use of this property to test what's happening for critical number. For example, let's say if x naught is a critical number, let's say that if you compute the f double prime at this point, let's say it is positive. So what does it mean? It means, locally speaking, we expect that the shape around this point for the line is concave upward. That's the meaning of concave upward. And it automatically implies that at the point x equals x naught, it is a local minimum. If you evaluate the f double prime, which is the second derivative at the point x naught, and get that it is a negative value, so we expect that around this point, the shape of the graph is concave downward. So you're getting a shape like this. It means that at this point, x equals x naught, we expect that we'll see a local maximum. And there's an extra question here. Please note that if f double prime at a certain critical number is 0, there's no conclusion we can draw. So we probably need more details about this point to understand the behavior x equals x naught, what's happening over there. But anyway, now let's do an example. So let's look at the current example together. You're given a function. You're asked to find the behavior around certain critical numbers based on the use of the second derivative test. The first step is to find all the critical number first. So you need to find f prime. And in this problem, f prime is the same as 4x cubed minus 16x, right? And all the critical numbers x can be obtained by solving the equation by setting it 0. And I believe you're able to solve this problem. So what you get, the next step is you can pick out the 4x as the common factor. So it means that x can be 0, or x squared minus 4 can be 0. In that case, it means x is either positive 2 or negative 2. So altogether, there are 3 critical numbers. And instead of using the first derivative test, let's try to use the second derivative test now. Let's look at the f double prime, which is the second derivative. It's gonna be 12x squared minus 16, right? And now you don't have to draw the sign table of f double prime. Instead, we can directly evaluate the f double prime at the 3 points here. So let's do this exercise together. So that's the evaluations that you can do based on the 3 points of critical numbers and also the f double prime expression. And now you see, first point is x equals 0. We evaluate it for this point for the f double prime, and we get a negative value. It means that we expect that around this point, it is actually a concave downward shape. And for the last 2 values, they are positive, so we expect that at these 2 critical numbers is a concave upward shape. It is good that f double prime is not 0 here. I want to repeat it again. If f double prime is 0, there's no conclusion that we can draw based on the second derivative test. So you see, now we basically get the answer. The answer is we actually have one local maximum, which is the point when x is 0. 0 is coordinate, f of 0 is the y coordinate, 0, 1. I'm doing the evaluation by using the original function of f of x. which is like this, which is 1. And similarly, we actually get two local minimums. The first local minimum is the point 2, -15, and the next one is -2, -15. So these are the behavior around these critical numbers. One is local maximum, the other two are local minimums. And you can see that the second derivative test is quite handy and very convenient if you're able to find the f double prime quickly. And sometimes, depending on the function f, it may not be that easy, the f double prime. So we may just make use of the first derivative test and the corresponding sign table for the f prime instead of using f double prime. So that's the end of this video.